Buenas tardes, estimados aprendices.
Buenas, mister.
Again, hope you're doing well. All right, guys, going to start with a new lesson physics. All right, and you're going to see though it can be possible. We're studying circles and geometry. We're going to study physics and physics circles again. Yep, you're right. In this situation, my dear students, we're going to learn how what will be the behavior of that rotational motion. So actually, 2 quarters ago, we learned how to, we learned or we studied what was the behavior for the body, so or any particle who's moving in horizontal path, in a vertical path, and also in 2 dimensions. And 2 dimensions, I said, what we're talking about the projectile movement or 2 dimensional motions, right? That happens with moves at the same time, the horizontal and vertical situation. We studied the laws of motion, the explanation why this movement, the word energy and power. This is the reason what happens with the movements. The objects is moved on one side to another one. They're creating energy. And also, we learned the different kind of principles of conservation of movement in the collisions, elastic and inelastic collisions in 1 and 2 dimensions. But today, we're going to learn one singular another motion that we use and we get used to it. Actually, for example, the rotation of rigid bodies or rotational motion. As soon as you can see, if you move your head on the roof, you're going to see the fans. There's a one established, one singular position, but they have a rotational motion, right? So in this rotational motion, my dear students, we have 2 kinds of rotational motions. One of them is given by a constant speed, and another one, obviously, with the constant uniform angular acceleration. And you're going to see in this class, it's like a extension of the first 2 lessons or the first 2 lessons, the first quarter, when we studied uniform speed and uniform acceleration, because we have 2 kind of acceleration. Actually, yeah, 3 kinds. The first one is the tangency acceleration. It's the normal acceleration we find out for any object that moves in straight lines by one hand. By the other hand, we got the centripetal acceleration. We're going to learn about distance later. This is the acceleration who brings any objects to the center. And the angular acceleration. This acceleration provides when the object moves in circular motion in one precisely object. Okay, so to start the working about with the movement with the constant angular speed. Constant angular speed. We're going to talking about for one singular piece of distance according from the around this circle. Okay, this lesson we're going to learn in geometry a few lessons later, but using the geometry principles. But in this case, we're going to learn this lesson in physics applying the trigonometry principles. If you see, you can imagine the circle, right? And around the circle, we have 2 lines that connect the distance between the center for any part of the points of the circle. Remember that we're talking about the radius, because a circle is a set of equidistant points at the same plane, right? Between them, you can see there's going to be an angle. Not necessarily will be 90 degrees, could be any angular displacement or angle, right? And if you see this connection between these 2 radius in this purple way has a form of the slide of pizza, right? You can, if you have some imagination, you can draw the piece of salami over here, or yummy yummy one here, or the little one here, and so on. You got the slide of pizza. Okay, but this is not important thing. The important thing is what is the name of this part of the pizza. This is the cheese age of the pizza, right? But this case, this cheese part of the pizza, in this case, in physics terms and geometry terms, this is when we're talking about the letter S. And the letter S, my dear students, is represented by the arc length. In Spanish means longitud de arco. Why? Because we have a smaller arc in that situation. So before to start to looking for the another space, obviously this the last picture, this red points, it's irrelevant. Just for I was giving you an explanation just so you can identify the peak of the slide of the pizza. There's gonna be located the central angle. Their size of the slide of the pizza will be the radius, and the part of this located the cheese bar, the pizza will be calling the arc length. So arc length, arc length. How we can calculate the arc length? The arc length in physics definition, the letter S, can be obtained multiplying by the radius r multiplied by the angular displacement or the angle. So where the S is representing the arc length, R represents the radius, and theta will be the angular displacement. The angular displacement. What will be their measures? The arc length, the measures will be given in meters, radius in meters, and the angular displacement, the name of the unit is radians. Why radius? Because the maximum measure of the radius is approaching to the unit circle. I mean, the radius 1 or the values from the pipe. Yeah, that constant value has a value 3.14 and 16. That's why this is how we're going to obtain the angular displacement. So if I mention the angular displacement must be set off in radians, okay, we really need to know some conversions. Conversions, okay, of units. So, for example, the first conversion we have to learn is how to change degrees to radians. It's simple. To change degrees to radians, my dear students, there's a simple postulate. The only thing that you have to do is multiply x quantity degrees by pi over 180 degrees. And that's it. This is going to be the process to change degrees to radians. For example, we have 30 degrees, 30 times pi divided by 180, and you got the quantity of radians. So the opposite, how we can change radians to degrees. That will be the opposite. For example, if you give you 4 radians, and we really need to know, I really need to know what kind of degrees we have. Okay, the only thing that we have to do is multiply the quantity pi over, okay, x pi radians, right? Multiplying by 100 over pi degrees. And this is going to be the same situation. What is going to happen? The pi with pi will be canceled, and you can multiply, well, actually the number by the number, or simply if you don't have this pi, we're going to go to just like this one, will be better. X radians. multiplied by 180 and divided by pi. All right, is the opposite. Okay, and the third chance to change is how to change uh, change radians. Number three, sorry, radians to revolutions. To revolutions. Revolution, that means lambs. All right. It's simple, my dear students. This is a conversion. One revolution that will be equal to 2 pi radians. And that's it. Okay. Because the angular, we must to make sure the angular displacement in this lesson always that's supposed to be written in radians. But at the beginning of any problem could be given in many presentations. Could be in the regular presentation that's supposed to be radians, could be degrees, or could be in revolutions. That's why we really need to know how to transform it or change degrees to radians or radians to degrees and change radians to revolutions. All right, this is the conversion of the units. Meanwhile, because we are assuming that at the beginning, this circle is moving with the constant angular speed, okay, we're going to have a arc length. I mean, the lateral displacement from the circle is a product between the radius times theta. Theta represents the angle of the angular displacement, and make sure always this angular displacement must be set up in radius. Okay, what else? How we can calculate in another situation, how we can calculate the angular displacement. Obviously, constant angular speed. Remember, constant angular speed, that means we have the same speed without acceleration. Well, actually, if you remember in physics, when we really need to try to find out what will be the distance of displacement with a constant speed of velocity, distance that will be equal the product between velocity times time, right? Well, in the rotational motion will be the same, but instead to say the distance, we're going to use theta. Theta who represents the angular displacement, and that will be the product between omega is a letter W with a horizontal line over here, multiplying by the period of time. All right. And what does that mean, omega? Remember omega, and I'm going to write over here. Omega will be represented by the angular speed. The angular speed. This angular speed is the units will be given by radians per second. The period T represents the period of time, right? It's represented by seconds. And theta is the angular displacement, as soon as you can see, my dear students, is given in radians, but it could be given in radians, degrees, and revolutions. But remember, make sure always theta must be set up in radians. So for this lesson, my dear students, every time that we want to use the calculator, please set up your calculator in radians mode, no degrees, because of the moment we're going to use function like a sine and cosine, if you have set up the calculator in degrees, you're going to have some problems because they're going to have different answers. So what is another way of saying to calculate omega or the angular speed? Yeah, the angular speed can be calculated divided by the value from omega divided by the period of time. But there is another situation, another relationship. The value from omega also can be calculated and multiply the synchrone periods 2 pi multiplied by this capital F. This capital F, my dear students, is represented by the frequency. This is going to be the frequency. The frequency is the number of revolutions given by the number of revolutions per second. Sometimes in some textbooks, instead to say hashtag yes, you can give it this by the symbol RPS or RPM. RPMs, that means revolutions per second. RPM means revolutions per minute. All right. And remember, the frequency can be calculated by the quantity of revolutions by the period of time. For example, if you have how to say that, at this, who is moving 20 revolutions in 4 seconds. Okay, if you divide 20 divided by 4, that will be 5. Okay, the frequency will be 5 revolutions per second. And also the period of time can be calculated by the reciprocal value of the frequency. I mean, 1 over frequency. For example, if the frequency, we're talking the last problem, 20 divided by 5, that was 4, 4 revolutions per second, the period of time will be 1/4 of the second. I mean, the reciprocal value of that answer. And remember the units from the period of time will be seconds. The period of time that represents the total time for one singular body who's complete one revolution. I mean, who's complete one lamp. All right. This is that real, at least for a while, the relationship between the rotational motion, arc length, angular displacement in function with theta and W omega can be calculated multiplying 2 pi times frequency. And after that, my dear students, we have another relationship. This another relationship is given by the relationship between angular speed and tangential speed. Tangential speed or linear speed or velocity, the normal v. So if you really need to know how to transform, how to find out the linear velocity between in relationship with this angular speed, it's simple. The only thing that we have to do is velocity or linear velocity that will be equal to multiply omega times the radius, into capital R, times the radius, right? In this situation, we can transform, for example, 20 radians per second. If you have a radius for 2 meters, all right, 20 radians per second, if you multiply by 2, you got a linear speed of 40 meters per second. All right, this is the another relationship between them. Now, if you ask me, okay, mister, but if we have a linear velocity or tangential speed of velocity, what happened with the acceleration? There's a relationship between them. Of course, we have this relationship between angular acceleration and tangential acceleration. There it is. This is just like a conversion if you want to see in that perspective. All right. This linear acceleration or tangential acceleration given by only the letter A, the normal A that you know, and that will be the product between, yep, this angle, that means alpha multiplying by the radius. Alpha multiply the radius, where alpha representing this angular acceleration. Angular acceleration given in radians per second square. All right. This is when we have some kind of acceleration. So, but this is going to be the behavior with this circle if and only if the moments representing by constant angular speed. But what happened if the angular speed of velocity is changing? Well, that happened. In this case, we're going to have a constant angular acceleration. Constant angular acceleration. Constant angular acceleration. Obviously, we won't have the same speed of velocity. So if you remember, in the uniform acceleration, we have four equations. And I think you have the raise your hand and your notes in the first quarter, the formulas. The first one was distance equals final velocity plus initial velocity over 2 multiplied by time, and so on, right? Distance equals 1/2 acceleration times square plus initial velocity times time. Another formula is final velocity equals initial velocity plus acceleration and time. And the last one, final velocity second power equals initial. Ya me cansé. Este bicho jodido sí molesta. Sorry. Final velocity second power equals initial velocity second power plus 2 times acceleration distance. Yep. If you ask you, the Mr. Buta asking always, we must memorize those formulas. And I could bet on you if this gentleman, he doesn't know the formulas, he didn't memorize all of them. Well, you should see I memorized all of them because of many years of doing that situation. But you got to raise your hand the formulas on index card or create a special notebook where you're going to have those formulas. Well, just a matter of speaking, the angular acceleration, the formula will be the same. But instead to use distance, we're going to use the first one. We're going to use theta equals final angular velocity plus initial angular velocity divided by 2, the period of time. This is going to be the first one. The second one, theta could be equal to 1/2 alpha times square plus initial velocity multiplying by the period of time. If you compare these two ones, are so similar with the uniform acceleration. The changes, instead theta is distance, instead alpha is the letter A, and instead W sub zero, we have B sub zero. The third formula, we're supposed to have a final velocity equals the initial angular velocity plus alpha period of time. In the number 4, the formula number 4, we got the final velocity, omega, second power equals omega at second power plus twice alpha times theta. And we have the four formulas. We're going to use if and only if the problems represent angular accelerations. And you're going to ask, well, Mister, there's a possibility, just like in the first quarter, that we have some problems when we combine a constant speed with a constant acceleration. The answer is yes. Just like this is going to be a special review, not reviews. So a remake, if you want to say in that situation, of the first quarter. With the difference this time, instead you use those letters, we're going to use angles because alpha is in the module the student says pescadito. I don't know why they're using that term, but this is the angle alpha, theta. The another one is omega. We're going to use angles. That's why we have a rotational motion. Okay. And after that, we're going to study the circular motion. In this case, we're going to learn how to calculate the centripetal acceleration, the centripetal force, the, the conic pendulum, the angles for the curves. And we're going to finish with the Kepler's law. But meanwhile, but at least this today I'm giving you an introduction for the rotational motion of this stops. Tomorrow, we're going to solve problems according to the rotational motion. And it got wheels the next week and another week. We're going to study the rest of the chapter. I mean, the uniform, the centripetal acceleration, force, conic pendulums, frequencies, and Kepler's law. So I don't know if you have doubts or questions to this for, or everything's clear. Remember this conversion of units. Please take a note because we're going to use this conversion just like a table one. Preguntas. Aquí no hemos hecho
No, mister.
ejercicios. Bien. Aquí no hemos hecho ejercicios. Solo fue una clase. Y yo quiero explicándole las fórmulas, cómo se usan las fórmulas para que vean esa longitud de arco. Es como si tuviera una pizza entera y te reventara un slide de pizza. El pico de la pizza, la parte más delgadita, es donde está el ángulo central, y el lugar donde se pone la orilla de queso de la pizza viene siendo la longitud de arco. Bien. Bueno, entonces, mis estimados aprendices, si no hay dudas, no hay preguntas, si todo está en perfecto orden, pues entonces lo vamos a dejar hasta aquí, a no ser que alguien más tenga alguna otra consulta. Y sí, esta parte, longitud de arco, lo vamos a ver en dos perspectivas. Aquí primero en trigonometría, porque esto es parte de trigonometría, lo vamos a ver en physics. Y en geometry, si Dios quiere, en 1 o 2 semanas lo vamos a tocar, pero eh, no vamos a usar radianes, sino que hay una pequeña conversión entre los grados, pero al final la respuesta es lo mismo. Bueno, entonces, si no hay dudas, está todo claro. Entonces, podéis ir en paz, muchachos. Cuídense. Bye bye. So
Bye,
long.
mister.
Take care of yourself. I send a picture in the WhatsApp group. Don't worry about it. Take care of yourself.